Hi there. In this video, we're going to talk about combining like terms to solve equations. The first thing I want to talk about is the difference between expressions and equations, okay? So an expression is a mathematical statement, all right? So mathematical statement involving operations, all right? So involving operations. So for example, if we're talking about an expression versus an equation, I would come in and I would say that an expression would be like 3x plus 2, or, and that's an example, 3x plus 2, or I would say like 5y minus 7. Okay, these are expressions, all right? And it's when you're involving addition, subtraction, multiplication, and division. All right, and an equation is when two expressions are equal. All right, so two expressions are equal. All right, so for an example, like if I were to set up an equation, I would say 3x plus 2 is equal to 7. Okay, notice that even though 7 isn't necessarily an expression, I could certainly put an expression in here, but it's when two things are equal. And most likely we see some sort of expression on one side of that, all right? So the difference between expressions and equations is that expressions we evaluate, okay, and simplify expressions, all right? And in equations, we solve them, all right? So we solve equations. And so it's really important that we understand the difference between the two so that when we move further on down to solving equations and simplifying the one side of an equation and doing all that kind of stuff, that we know the difference between the two, all right? So let's first talk about what a solution to an equation looks like. Okay, the next thing I want to talk about is solutions to equations. So a solution to an equation is a value that makes an equation true. So I'm going to use a very simple equation here, and I'm going to call this, x plus 3 is equal to 7. All right, and so, what we want to think about is some number plus 3 is equal to 7. What's that number? Okay, and we can think intuitively about it, and we can say, well, I think x is equal to 4, because 4 plus 3 is equal to 7. So if we plug that in, 4 plus 3 is equal to 7, does this statement, now that I've replaced my number with my variable, does that make it true? All right, and so if we think about it, 4 plus 3, well, that does equal 7. So we get that 7 is equal to 7, and that's a true statement. Therefore, this is my solution, okay? And so when we are solving equations, okay, to come up with our solutions, what we want to do is we want to use opposite operations, okay? And we call these also the properties of equality. So let's first think of something here. All right, let's think of an example, and let's just think of a true statement. So I'm going to write down that, say, 10 is equal to 10, and I'm going to do that 4 times. Okay, and so above this, what I'm going to do is I'm going to write add, subtract, multiply, and divide above each of those, okay? And so we all agree that 10 is equal to 10, that this is a true statement. All right, so if I were to do something to my first example, and let's just say that I wanted to manipulate this somehow, and let's say I wanted to add 2 to the left side, all right, the only way that I'm going to keep this balanced and keep this equal is to also add it to the right side. And when I do that, what I'm doing is I'm going to get the statement that 12 is equal to 12, and that continues to be a true statement. All right, same thing applies for subtraction. If I subtract something from both sides, all right, or from the left side, I have to do it to the right side. And when I do that, 10 minus 3 gives me 7, and that's equal to 7, and that's all stays a true statement. Okay? If I multiply both sides, so multiply by 2, then we get that 20 is equal to 20. That still remains a true statement. All right. If I were to do division and divide both sides by 2, then I get the statement that 5 is equal to 5, and that remains true. So what I'm doing there is that these are the properties of equality, all right? And what it means is that what I do from on the left side, I have to do on the right side, all right? So when we solve equations, we operate on both sides of the equal sign. So both sides of the equal sign. All right, so if I start manipulating this and I start adding or subtracting, multiplying or dividing, I have to do it to both sides in order to stay balanced. Okay, and so now what I want to do is talk more about like using these opposite operations and reverse PEMDAS to solve some of these equations. All right. And so the example I want to think about is the one we just talked about, all right? And what this is going to be is that if I have, say, some number plus 3 is equal to 7, what's that number going to be, all right? And basically it's going, well, what's x equal to, all right? That's the question we're asking ourselves. So you can think intuitively about it. We know that the answer is going to be 4, all right? However, how do we use the numbers 3 and 7 to get 4 out of this? And so if you think about, well, if I were to get x by itself, if I did the opposite of adding 3 to both sides, then that allows me to then subtract 3. And if I do it to the left side, I have to do it to the right side. All right, and so from there, 3 minus 3, I do the math here, that becomes 0. And I'm simply just left with x on the left side. And then I have 7 minus 3, which gives me 4. And that's our answer, and that's how we figure this out, okay? And that's what we do. So I always want to look at what the equation says, and I want to do the opposite of what it's telling me. Now, on this example, we have this equation that we're trying to solve for x. X minus 2 is equal to 7. Some number, take away 2, gives me 7. We know that the answer to this is going to be 9, okay? Because 9 minus 2 gives us 7. 7 equals 7. We're good. Okay. However, using algebra, what's the opposite of subtracting 2? And that would be to add 2 to both sides. And when I do that, negative 2 plus 2 adds to 0. That goes away. We drop down our x and we do the math on the right side. 7 plus 2 gives us 9. Okay. And that's the answer that we were looking for. All right. Now, on an example like this, you have 3 times some number gives you 12. And if you think intuitively about it, we know that the answer to this question is going to be x is equal to 4. All right, but what I want to do is think, well, let's do opposite operations and move this 3 to the other side. What I'm seeing is that I have 3 times some number x. To move that 3 over and isolate x, I divide both sides by 3. So let's divide by 3 here and divide by 3 here. And what you get is you get 3 divided by 3, which is 1. All right, so you're left with 1 times x is equal to 12 divided by 3, which is 4. Now, 1 times any number is simply just that number. So 1 times x is going to be x, and that's equal to 4. And that's what we're looking for. And we can check and say, does 3 times 4, is this a true statement? 3 times 4 is 12. 12 is equal to 12. That's true. So therefore, we're good. Now, in this next one, you have this equation that says some number, you divide it by 5, and you get 3. Thinking intuitively about this, I can just say, well, that number is going to be 15, because 15 divided by 5 is 3. But let's think about what we could do to move this 5 to the other side and think about the opposite operation. So if I'm taking x and dividing it by 5, the opposite of division is multiplication. So I can multiply both sides by 5. And on the left side, you have 5 divided by 5, which is simply going to give you 1. Multiply that by x, and then you've got 3 times 5, which gives you 15. Now, 1 times x, 1 times any number is just that number, so you're just left with x on the left side, and you've got 15. Okay, and we can always check, and we can say, all right, well, 15 divided by 5, does that give us 3? And 15 divided by 5 is 3. 3 equals 3. That's true, so we're good. Okay? Now, you guys are probably thinking to yourself, well, this is really easy. Why does it matter that we go through all these easy problems? Well, the answer to that question is that these questions will get harder. Okay? So let's look at a harder example. Now, on something like this, we call this a two-step equation. okay? And when I have something like this, I'm saying 4 times some number, subtract 3 gives me 13. This one's a little bit harder to intuitively think about it. So what I want to do is use my properties of equality to isolate x and solve this equation. The first thing that I'm going to do is I'm going to do the opposite of PEMDAS. I'm going to add or subtract first. And I'm going to move this negative 3 to the other side. So if I'm subtracting 3, the opposite of subtracting 3 is to add 3 to both sides. And what happens is negative 3 plus 3 adds to 0, cancels out, drop down your 4x, and you're left with 16. Now, I have a one-step equation, and we're back to where we started. 4 times some number gives us 16, so I'm going to divide both sides by 4 and isolate my x variable. 4 divided by 4 is 1. We're left with x. 16 divided by 4 is 4, and that's my solution. Now, we can always check our solutions, and we can do 4 times 4 minus 3. Does that give us 13? Now, 4 times 4 is going to give us 16 minus 3. Does that give us 13? And we get 13 is equal to 13. That's true, so we're good, okay? Now, on an equation like this, where we've added in another step, okay? And this is the combine like terms step. And so I wanted to make sure that we went through all the other kinds of things before we just straight up jump into this, okay? So when I'm trying to solve this equation, what it's saying is 4 times some number plus 3 times that same number minus 7 is equal to 21. These get harder and harder to think intuitively about. But what you have to do is use a couple of things to simplify this and then work our way down to easier and easier equations to solve for x. So what I want to do first is combine like terms. And my like terms are like because they both contain an x, okay? If I had numbers, then I could just add those numbers or subtract those numbers. But on something like this, I want to just combine those. And how I do that is I take my numbers that are out front, add those together, and then keep my variable x. So in this case, 4 plus 3 gives me 7. Keep my x, and then write out the rest of my equation. And at this point, what I have is a two-step equation. So now I have the question, all right, well, 7 times that number minus 7 equals 21. What's that number? So what I want to do here is then do my opposite operations. I'm going to add 7 to both sides. 7's going to cancel out, add to 0, and we're left with 7x is equal to 28. Now, the opposite of multiply by 7 is to divide by 7 on both sides. So you get that x is equal to 4, okay? And that's how we would solve those kinds of equations. Let's look at one more example. All right, so these questions just get a little bit harder. And so think about it this way. All right, let's read this equation and understand what we're being asked to do. I have 8 times some number p minus 2 times some number p minus 3, add 8, and that's going to give us 23. What's that number? These get harder and harder to think about, so it's important that we understand the steps involved to solve an equation like this. The first thing I want to do is combine like terms, all right, to simplify. So I'm going to combine 8p and 2p, and then I'm going to combine negative 3 and 8. Now 8p minus a 2p, remember, operate with your numbers out front and keep your variable. So 8 minus 2 gives us 6p, and then we're just going to add our numbers here, negative 3 plus 8, which is going to give us a positive 5. All right, so plus 5, and that's going to give us 23. Now I have a two-step equation here, and all I'm going to do is subtract 5 from both sides. All right, this part's going to add to 0. 5 minus 5 goes to 0. Bring down your 6p. 23 minus 5 is going to give us 18. Now, the opposite of multiplying by 6 is dividing both sides by 6, and we get that p is equal to 3. And that's how we solve these kinds of equations. That's all I've got for this video. Please reach out with any questions, and we'll see you soon. Thanks. Bye!